quick little synopsis about Total Seal. We've been around since 1967. Started out in what we affectionately know as Joe's Garage. Like many companies, started in a garage back in the day. You know, Mr. Gasket, all those stories you heard about him cutting gaskets out of the back of a wagon. Our story's kind of the same. We started out, you know, in Joe's Garage and have grown it since. We've been in this building since late 1999. It's about 25,000 square feet under roof, and we're going to walk in and kind of show you how it's done. Come on in. Natalie, the world, Natalie, our receptionist, par excellence. She's getting married soon and going to Maui. We've been strategizing the event, and I think she's going to hit every possible thing there is to do. Awesome. So we're heading out to the shop. These are production offices, purchasing. Rob's office, he's in charge of the shop. And we've got production managers in here, maybe out on break. Oh no, they're having their production meeting, 10 a.m.
Oh, that's right.
That's why the offices are empty. So we're going to walk you out into the shop. As you can see, no admittance, but you're allowed today. So we're going to take in and show you how this is all done.
Certainly the magic takes place.
Yeah. So to talk a little bit about what we do, there's basically two materials that you're going to work with when you manufacture piston rings. You're going to have irons, whether that be cast iron, ductile iron, hardened iron, martensitic irons, or you're going to have steel. And that's how it starts. Now, me personally, it's a back scratcher. But this is also a piston ring. It's dual purpose. Has two functions.
It will become a piston ring.
It will become a piston ring. So we're going to show you a little bit about how this is done. Now, the one thing we are not is a foundry. We don't pour metal. We don't make metal. So we're always having metals done all around the world. We use foundries all over the world. We source steels from all over the world, primarily out of Japan. But I want to show you how an iron ring starts life. You can start with an iron ring out of a thing called a cuff, which I'll use this piece of PVC as an example. Kind of looks like that. It's kind of a rough casted iron tube. You ID it, OD it, slice it, and that's kind of how you did rings back in the old days. So you could actually use cam turning lathes, and you would produce it literally out of a piece of pipe. The problem with that is, one, it's slow. Two, there's a tremendous amount of scrap. You actually get rid of or have to recycle more material than you actually end up with. So this is a very old school way of manufacturing rings. Today, they're investment cast. We have the rings brought to us in what we call a semi-finished state. They get poured, they get rough ground, and delivered to us in a semi-finished state. This allows us to do the finish work on the part. We have very, very little scrap material. It allows us to ID it, OD it, bring it down to size. We can make multiple sizes out of one semi-finished part. It allows us to produce parts very quickly, very efficiently, and we'll say that's the modern way of working with iron rings. At least it is for us. So now we're going to kind of walk you back into the back, and but while I say that, we're going to stop for 1 second. This is lathe operations through here. We have multiple CNC lathes. As you can see, lots of aluminum. It all gets recycled except for what I dump on the floor. We build our own leak down testers, ring compressors, ring squaring tools, lapping sleeves, all the quote unquote lathe type operations that would be done are done in this area. But now we're going to walk to the back of the shop and show you where we work on the iron based rings. Yeah.
Save the best for last, right?
Yeah, what Lake was saying there, that's going to be that's the par excellence. So as you can see, if you want to, this is lathe operations. This is manual lathe operations through here. A lot of our rings are actually cut by hand, one at a time. We'll bring them into size, rough them into size, cut them down, bevel them, cut them for gapless, put a face profile on the iron, because this ring, there's no bevels, there's no barrel. This is just a chunk iron. I would say by the sound of this one, that's a ductile. There's a little tip for you as well. If you take a ring, if you're not sure what you have, you can take a piston ring and you can drop it on a table and get a sound. If it rings, which that one did, instead of just a dull thud, that's going to tell you it's a higher tensile material. The higher the pitch the ring, typically, the harder the material. A ductile iron ring will ring. A cast iron ring is just going to go thud. You're just going to get a dull thud. So kind of a handy little tip if you're not sure what it is. A lot of noise in here, it's hard to hear, but that has a nice little ring to it. That tells you it's made out of a hardened material. So we've got manual lathe operations through here. But we're going to come to the old workhorses of the shop. Hi, Kwan. Say hi, Kwan. These are our old workhorses and our workhorses throughout the industry. These are Katokas. These are, everybody knows the word CNC. These are NC. These are numerical control machines. What this machine will do, if Blake wants to take a look here, we've actually got some product loaded up. This machine will do the one thing I ask it to do. I can load it up with semi-finished parts. I could load it up with a cup if I wanted to load it up with a cup. It is going to do the one thing that I ask it to do. It can come in with a parting tool and part the parts off. It can come in, put an inside chamfer on the ring if I want to put an inside bevel. It can come in if I want to make a gapless cut. It can come in and make a gapless cut. As an example, actually, here's one that was being cut for gapless that came off this machine. So it's going to cut one ring at a time. It's going to drop in. It's going to come out the chute, land in the tray, and we've got a part that's just been machined. So how we work with these machines is we actually ping pong just like a ping pong table. We're going to come off this machine with an operation, and we're going to go to the next Katoka over here. As this one's being run, this one's being set up for the next operation. This one will get loaded up with the rings that just came out of this one, and whatever that next operation is, could be putting a taper on the face of the ring, it could be putting a barrel on the face of the ring. It all depends on the tool that I put in here. It's simply going to come in, make the cut as it's programmed, and it is going to do that one thing that I ask it to do, and one thing only. And we can sit here and bounce back and forth, cut it on this machine, cut it on this machine, next operation back to this machine, and sit here and bounce back and forth all day long. We can typically do about 1,200 rings a day off of these two machines. We actually have a third one upstairs, an old parts donor, that we were actually going to put into place at one point in time, but because of the cost of buying another, because you really want them in pairs, that pushed us into the world of steel ring manufacturing. When we looked at the cost of buying a new Katoka, because you can still get these, it took us into a whole other world, and we'll talk about that here in just a couple of moments. This area right in here is the EDM area. So when we cut our rings and we cut our oil ring rails, we use a wire EDM. Most companies use a saw, literally looks like a big bandsaw, and you end up with those kinds of cuts, fairly large, fairly rough, fairly uneven. We use wire EDMs. It's a slower process, but it's a much tighter tolerance process. We can go with a much tighter ring end gap. As you can see, there's actually oil ring rails down inside that sleeve. I don't want to stick my finger in there because this is electrically charged wire in an ionized water. And we're actually burning the end gap into a sleeve of rails. And what we've got, if you want to take a look here, John set this up for us so we can show you a little something. John, the world, John. These are oil ring rails. And you remember that toy you had as a kid?
It walks downstairs alone or in pairs and it makes a funny sound.
And if you can catch it, there's the other end of a slinky. These are a slinky. We coil these. These have been chrome plated. Again, just like chrome, you chrome in the bumper on a car. We do them with no chrome. We do them with chrome nitride, titanium nitride. We offer multiple coatings depending on what the cylinder material is, but that is how your oil ring rails start. They're going to put into a sleeve, and they're going to be, that is set to the bore size. I think that one said 4-inch. Okay. Excuse the bad eyes. And we're going to come in with the EDM, and we're going to cut from the inside to the outside and cut the gap in the rails. You can do this with compression rings. You can do this with anything you want to put in there that you want to cut. But this is how oil ring rails, they are simply round wire coiled, and then they get chromed, and then they get cut. And you've got an oil ring rail. Awesome. So we're moving more into the heart of the shop. So we've looked at EDM, we looked at how the parts are cut, the end gaps, oil ring rails, iron rings. This area right here is what is known as OD lapping. So the thing that you want to remember, back in the old days, if you remember, you put your rings in your car, in your engine, I should say, and they would tell you 5,000, 7,000 miles, because you have to actually lap the surfaces in the final honing process or machining process in the engine. After we've done our cylinder honing, after we've done all our prep work, is the two surfaces have to wear in together. Just like, brake pads to a fresh rotor, a flat tappet lifter to a camshaft. The surfaces have to mate together. So the problem is, if you take just an old flat ring, we've got this phenomenon in the piston referred to as piston rock or rockover. The piston always tips over top and bottom at top and bottom dead center. So we actually want to put a barrel on that ring. We don't want to have to let the engine wear all that in. That takes a lot of miles. So again, back to the old days, it could take 7,000 miles, 5,000 miles to get your ring seated up. Well, it's because we're using the cylinder as a lapping sleeve. But what we like to do here, what we do here, is we're going to do that ahead of time. So we OD lap our rings so your cylinder, or engine in this case, doesn't have to do it. So we'll come on over here and I'll show you how it's done. This is Will. Will the World, you're live. He's loading up a lapping sleeve right now. As you can see, these look like cylinder sleeves. He's loading one up. The big clamp is what is basically a big ring compressor that allows the rings to get into the sleeve. These are the lapping sleeves right here. Basically look just like a cylinder, honed just like a cylinder. They've got a little spiral grooving that helps them to hold the lapping compound. Now we're going to put a mild abrasive in there. This gray slurry, when Blake comes back around, this gray slurry you kind of see here is actually an abrasive. That's actually a diamond abrasive that goes in. And depending on what we're trying to do to the ring, what the material of the ring is made out of, cast iron versus stainless steel versus tool steel, what that ring is going to determine how many cycles or how many strokes that ring goes through. And as you can see right now, we're doing what your piston would do in the engine. Now, granted, at a much slower speed, but we're actually OD lapping the ring.
Breaking it in essentially before we even tip it to you.
This is the pre-break-in, break-in. But as you can see, it's not the fastest process in the world. And we kind of get towards the tail end of this. We're going to show you, the newest equipment we've brought to the shop. We've actually got two of these lapping centers right here. And as you can see, again, we're talking the slurry. We've got a diamond abrasive slurry here. And depending on what we're trying to do, a cam plate or wave plate that's going to cycle the rings back and forth. If you think about it, kind of like a butter churn. We're just running those rings, cycling them back and forth. It what essentially is a big butter churn. So these are rings that have come through and are going through.
Again, this whole process is putting the barrel on the face of the ring.
This is putting the barrel on the face of the ring. You can also use it to deburr. If you wanted to, let's say you had a Napier ring. After you come in with a Napier cut, you can run them through the OD lapper just to take that little edge off, say, a Napier cut. Or if you want to just put a little deburr on the edge of the ring. It's all about how many strokes, how many cycles. Things like that are just a few little short cycles, or you get into longer cycles, putting the barrel on the ring, depending on the size of the ring, thickness of the ring, how hard the ring material is itself. Now, before we get into the next step, I'm actually going to diverge because we missed a step. And I wanted to see, as you can see these rings, see the discoloration right there.
Oh, yeah.
And what we're going to show you here, and I missed a step because I'm doing this in a different order than I normally do. So come on with me, it's just a few steps away. This is heat treating. We do all our own heat treating in-house. And as Blake will note, as we come in here, we're heat treating. So what you say?
Hey, don't touch.
Yeah, don't touch. You see, you've got a little bit of smoke coming out of there. Maybe we're cooking some pizzas in there. But this is the heat treating department. These are all rings that are going to go through heat treat at this point in time. This is an oxygen inert oven. This is nitrogen oven. So this is a tool steel goes through here. And again, oh, she's plenty warm. These are parts that have come out of heat treat. See the difference in the colors?
Oh yeah.
So over here we've got a plastic media for deburring the rings. The rings will go through a plastic media vibratory. This is a big shaker. The rings get deburred in here. This is black oxide coating. The coating that you would typically see on the top and bottom flanks of the rings, this is black oxide. This is an anti-rust compound. This is there. It does offer a little bit of lubrication in the groove, but its primary function is to just prevent rust when it's sitting on a shelf. Here in Arizona, we could put a garden hose on this, it wouldn't rust. But you take this to North Carolina in the summertime, rust is kind of a thing. So this is that coating, and some people will see different variations of the color. It's a little bit lighter, it's a little bit darker. That varies depending on the condition of the oxides, how long it's in the tank. The colors can range from a brownish reddish to a deep black. Just kind of depends on how long it's in the tank. The longer it stays in, the darker it gets. So when you see that color variation, nothing to worry about. It's simply there as a rust preventative. So, just wanted to step back in here so you guys can see a little bit of of some heat treating. So now we're going to go back to the lapping department. So we're OD lapping here. But one of the things that we do differently here is many companies use grinders. They'll use big grinding machines, Blanchard style grinders, double disc grinders, to get the dimension, to get the thickness on these rings. And it's a relatively fast process, produces relatively decent surfaces, decent tolerances, decent roughnesses. But one of the things that we've strived for here for years, and I'll just tell a quick story. When I first came to work for Total Seal, one of the first
years ago, by the way.
Yeah, 25 years ago, one of my first conversations was with Warren Johnson. And at that time, I knew about piston rings. I knew they were important. I knew they went in the engine. I've used them many times, but I didn't understand the importance of the tolerances and getting the specs where they needed to be. And my first conversation with Warren, I said, Warren, I realize, the brand of rings you're using in your pro stock stuff, if we could do something better, what is it we could do? And he goes, make me 8 rings that are all the same. And I said, well, what are you talking about? He goes, well, I buy 043 rings in a sleeve. He goes, my son, Kurt Johnson, an HRA Pro Stock, racer driver, multi-time winner, is sitting on the floor, miking all the rings and putting them in stacks and grading them. So I've got 8 of these, 22 of those, 16 of these, 14 of those. He goes, I would like to have 8 rings that are all the same. Well, one of the things we set upon on that quest is looking at how rings are made, how other companies do it, and with that in mind, saying we're not trying to crank out 100,000 rings a day out of here. So how do we make it better, not necessarily faster? How do we improve the tolerances? How do we do a better job? And that's really a big part of what we do here. EDMs for cutting the end gaps, OD lappers to get the barrel faces, as you can see, to get the face of the ring very nice. It's not a fast process, but it makes a very, very good ring. But the axial surfaces, and this one was kind of a bugger. It took a little while to get it, and we actually got a couple of patents on it, is we have a patented lapping process for getting the axial thicknesses. So come on in, let's show that to you. This is the lapping room, folks, and one of everybody's favorite places to work at here in the summertime, because again, remember me mentioning a few moments ago, it's going to be 110 degrees here in a very short period of time.
About 110 degrees in here.
This is 60 degrees year round. This is a climate controlled room because everything is temperature operated. We have to bring everything up to a certain temperature and hold that temperature to be able to hold the tolerances that we can hold off of our lapping room. So we're going to walk down here and say, we're going to say hi to Tyrone. Tyrone, the world, Tyrone.
Hi.
Let's go, Tyrone. So what we've got here is lapping machine. We've worked on these. We have multiple patents on these. You got conditioning plates in there, Ty? You get conditioning plates?
Yes.
Okay. So what Tyrone's doing right now is as these wear, they have to be conditioned. We have to get the flatness back in the plates because the plates do wear. But the other thing that we have to do every morning, as these have sat all night long, is we've got to bring them up to temperature, because just a couple of degrees of temperature variance and the tolerances go out the windows. So as you can see, these are lapping plates. These are what are going to hold the rings. Kind of looks like a big, what was that, spirograph we all played with as a kid. Ring's going to go in. We're going to lock the ring, and then they're going to go into the lapping machines. Hey, Tyrone.
Oh, the great thing you can see right here. You can see that.
I was going to say.
Right. So, top one is both moving to the left,
Lift that
the
one.
bottom is moving to the right, it's shut down.
Okay.
Essentially, grinding or lapping both faces simultaneously in opposite rotation.
Absolutely. So we're not just doing one side at a time. We're doing both sides at the same time. This way we can get an absolutely flat, uniform surface. And as like I said, you can see they're actually rotating the opposite directions.
Almost like centerless grinding, but for rings.
But for rings. And that's a beautiful way to put it. So coming off of these centers, a typical piston ring is held to a plus or minus 5/10,000 specification. So I'll throw out an 043 ring. A 43 ring is typically 42.5 plus or minus 5. That's considered an acceptable ring by most top industry.
It could be 043 or it could be 042.
Absolutely, anything in there is acceptable. Coming off the first stages of these lapping processes, we're holding plus or minus 1.5/10,000. So 1.5
10,000
is what's coming off these very first stations.
5 was your target. You're talking about 042.6 to 044.
Yep. And that's what's going to come off of these stations. Yeah. So we're also producing a very, very smooth surface roughness on that ring. We'll typically have RA numbers if you want to look at just a simple RA, which we always tell you not to do, but it's a quick, easy way to look at a piston ring. These will typically produce RA numbers in the middle to low teens. We can actually step our toe into high single digits coming off the early stages of the lapping process.
Well, we also use it to do the diamond finish rings.
Absolutely.
Right, as I know from measuring diamond finish rings at Jogies Racing, that they're like less than 2 RA. RA like 2 or less. And then like production rings could be somewhere 15 to 16.
Yeah, I agree. I've seen production rings from, so we'll just say some other suppliers with RAs in the 20s. So keep in mind that black coating that goes on the ring. I like to, if you put a lot of that on there, it can be kind of Bondo for piston rings. It covers up a lot of travesties. But there is multiple stations of this. So as we work our way further down the line, we work our way into the other stations. Now, coming off these stations, as Lathe just mentioned, the diamond finish line, we're going to come in and we're going to hold an RA of a 2 or lower. And we're able to hold tolerances of plus minus 50 millionths of an inch.
50 millionths.
Can we say that with a little loss of 50 millionths?
Yeah, exactly.
So we're able to hold extremely tight tolerances coming off of these stations. They kind of showing you some of the plates. We cut all those in-house.
All right, so everything we've shown so far, right, is essentially applies to a cast ring or a steel ring.
Absolutely.
Why don't we show them now how we make a steel ring and how that's different?
Or a great back scratcher.
Or a back scratcher, that's fine. One of the two.
Hey, Lake, I've got a question for you while you're in that room.
Sure.
Yeah, okay. So they're asking, with that lapping machine that laps the top and the bottom at the same time, is it only for square rings or can it be tapered rings too?
Yeah, any ring can go through there. Napier, tapered face, barrel face. There's actually rings that we do that are multiple combinations of shape. It's simply looking at the top and bottom or the flanks of the ring. That's the surfaces it's working on. So any of those rings can and do go through these machines.
Okay, super. Thank you.
All right.
So
this is about to be my favorite part of the whole deal, by the way.
So we're going from, again, 60 degrees. So in here, as you can see, these are lapping sleeves. These are OD lapping sleeves. There's literally thousands of them on the shelf.
Which, by the way, when we talk about honing, and why we act like we know about honing, it's because we hone a lot of sleeves.
These all get honed here, every single one.
And because these things use them up. Think about it. If you've got all these sleeves, you're looking at diamond quality people, you wear them out quite rapidly.
Very much so. So all of the sleeves, you know, let's say it starts out at, we'll just come here, 3-inch 480. Let's say that's where we started life. Once we've run this through a cycle of lapping, it's going to go to 3505 or whatever the next size is. So this one's right now sitting at 3511. This one's sitting at 3563. It used to be 3-inch 466, and then it was, before that it was 3-inch 426, 3389, and so on and so forth. They just keep getting honed out. So as you can see, 500 strokes on this one, 1,075 strokes on this one, 1,050 strokes on this one, 100 strokes on that one. So we record how many cycles have been on each sleeve, and then they get honed out to the next size. So as Lake said, we hone a lot.
Now, explain what all of this is up here.
Well, unfortunately, due to supply chain demands, all of this is a little less than what it ought to be. This is all steel ring material. Remember we talked about
Your back scratcher.
my back scratcher? Well, this is my back scratcher. Actually, my back scratcher is stainless. This happens to be M2 tool steel. But this is how it starts out life. This is a steel piston ring. It comes in a coil of wire. It's formed to the basic dimensions, and then we're going to cam coil it. There's different materials throughout here. There's stainless steel, there's M2 tool steel, there's 9254, which is a carbon steel. And if Blake takes a shot up there,
Oh, yeah.
you can actually see the copper stuff, and that's a product referred to as top met. That is an exotic material. It is a copper, nickel, silicon. We're always talking about material technologies, coating technologies. That's the latest thing that we're playing with in material technologies. For those of you that are familiar with a product called Axial, the old Chevy Vegas, 928 Porsches, Lamborghini, it is a silicon impregnated aluminum that is used to produce cylinder blocks, heads out of, that you don't require a coating. The ring in this case, the piston, would actually run on the silicon nodules. You polish those boards smooth, just like in the old Chevy Vega, until you expose the silicon nodules. Well, imagine that in a piston ring. This material is using the base material as copper because it removes heat incredibly well. In any performance application and even OE applications today, we're looking at trying to get the heat out of the engine as quickly as possible. Well, it lets us, quote unquote, step on the tune-up a little harder, eliminate knock in the engine, try harder. This material, once it sheds in, it beds in, it exposes the silicon nodule, and the silicon becomes the running surface. This is out there, it's been used, it's being tested right now, and this is the type of technology that is coming down the pipeline. Is it available and ready for you today? No, not at this point in time, but over time it will. So this is steel.
Incredible stuff, man.
Yep.
Just like you think about copper and kind of heat transfer, it's pretty amazing in what it can do.
It's neat stuff. It's been a learning curve. It reacts very differently than steels. It expands differently. It's not steel.
It's a learning curve. It's not drop in.
It's a learning curve, and we're getting there, and very rapidly. But so far, it's tested very well. But this is steel ring materials, and what we're going to do now is we're going to work our way over to our coiler. And this is where that flat wire becomes, well, that's not a good example, but a round piece. So coming in here, this is a cam coiler. So what we're doing, the thing you've got to remember, everybody, is a piston ring is not round. It's actually cam shaped. So when you coil a steel piston ring, taking it to this shape, you can do it one of two ways. You can round wire coil it, or you can cam coil it. Now, a lot of places will elect to round coil the wire. They'll make it round like we do for an oil ring rail. That's coiled round. But the problem you have there, and I shouldn't call it a problem, but what makes it a little more tooling intense is you now have to take it and heat form the ring. You're going to put the ring over an arbor to put that cam shape in the ring, and then heat treat it to put that cam that you've got to have in the ring. So you think about it right now, not round, now round. So the ring's only round in the closed form. So if you want to take a look, this is actually a cam coiler. We elected to develop a machine that will put the cam in the ring as it's actually running. We don't have to heat form or heat shape the ring to produce a cam shaped part. So that's one that's come off. Looks like you're doing setup right now. Yeah, so it's going through setup right now, getting ready to run the next, whatever the next work order is going to be. So we're coming out of the cam coiling section. And we'll come over, and this is profiling. So what we're doing here is we're actually taking the machine, the ring. It could be a steel ring, could be an iron ring, and if we want to put a profile on it, we can put a barrel face on it, we can put a taper face on it, napier it, we can put a combination face on it. This is actually using a cutting tool right now, but we also have a grinding head, so we can actually grind the face profile of the ring as well.
So this way you do a napier to it?
Yes.
Taper?
Yeah. This will do a napier, a taper. We can do combinations profiles on here, but it's traditionally used or typically used for putting a taper or napier style onto the ring. Oh, looks like perfect timing. This is the gap sizer. This is the machine that's actually setting the end gap. So this is a CNC gap sizer. It's going to take a stack of rings and it grabs them two at a time. And we're going to come in here and actually put the end gap on the ring. Now it can be debatable. Some people say we can hold plus minus 2 thousandths. Some say we can hold plus minus 3, but it's going to be between plus minus 2 and 3 thousandths gap coming off the CNC gap sizer. So what you've seen so far is we've seen, coiling of the ring, we've seen heat treating of the ring, we've seen getting the axial thickness on the ring, getting the profile on the ring, and there's more steps that we're going to come into as far as showing you some, testing, light tight testing, tension testing, things like that. But what we've taken here are the processes that we've developed and use every day, and we wanted to do this and build a automated cell. To take all of this and do it better, faster, and even more consistent. And you produce a more consistent part. And in this day and age, an automated cell only needs a couple of people to run it. So it's not as manpower dependent. So what we've got here, this is our newest toy. So everything you've seen now evolves its way into this cell.
We start here. This is the gap sizer, right?
Yes, this is the gap sizer. So we're going to load this up. Give me just 1 second. Hey, Aaron. Everybody, this is Aaron the World. This is the gap. This is starting end. This is the gap sizer. How many rings will this load up, Aaron?
The other day we ran 3,600.
So 3,600 rings through this the other day in one shift.
Yep.
So the rings are going to come into here. We're going to load the rings up. They're going to come down. Kind of walk us through it.
So it'll come down the conveyor, and then this is where the package separator is. You can do one ring all the way up to about 4 rings. Puts it through our grinder here. Oh yeah. And then the rings will come down the conveyor, push out, and then go through our wash stations here. And then it'll keep continuing to follow along. And then here's all of our deburring station.
This is all deburring, so essentially it's a big belt sander.
Right. Yeah. So essentially, we've taken a ring that was already coiled. Now we gapped it. Then you wash it to make sure it's clean. Then deburr it. Then it goes from there to the
We're going to the OD lapper. So we've got an elevator that's going to come up and bring the rings out of the gap sizer into the OD lapper, a similar system to what you saw in the other machines just a few moments ago. We're going to come down. These are the sleeves for this OD lapper, similar to the others, but much, much longer.
You can process more rings at a time.
Yeah, a lot more.
You get ready to change out the sleeve now.
Didn't think you'd be under this kind of pressure, did you, Aaron?
No, I didn't. you don't want to know things are going to surprise you. Somebody told me once that, it's right oil, right place, right time, right amount. So what it's doing now is it's dividing up the rings. We have about 60 millimeters is our overall stat, and then that will get put into the cylinder, and then it'll start ramming. The ram will start going, and then you'll watch the OD lapping in process.
In other words, here we go.
Yeah. For some reason, we got more. Okay. Because it's like them. So that's a good thing, right? It's others trying to tell us not happy about them. Yeah, they want a bunch of parts. Yeah, so you're right. So I can walk you through the rest of it, and then I'll reset the alarm. So down here is our first loss station. After it leaves the cylinder, it'll come down to here. This is our so it'll go through our first wash station, and then it'll slowly move down the line into our second and third, and then we have a hot box down at the end.
So it's going to not only gap size the ring, we're going to OD lap the ring, and then we're going to wash and we're going to dry the rings, all in one automated center. Well, thank you, Aaron.
And then from here, it's going to jump over the double disc grinder.
It is going to jump into the newest piece. Now, keep in mind, folks, all of this stuff, the piece on this end we've had for a little over a year. The gap sizer on the other end we've only had for a few months. This we've only had for a couple of weeks. So they're going to come out of here, and as we saw in the lapping stations in the back, we've got a new high-speed dual disc grinding system. This is going to come in and is going to set the axial height on the ring and do it at a speed that the lappers can't even imagine doing. Our goal for this cell, I know ultimately we're hoping to get 6,000 rings a day on this. We're told it can do 10,000 rings a day, which is going to be a game changer. It's going to allow us to produce a massive amount of product every day, and ultimately that's going to help us reduce costs and reduce prices. That's the goal here, is to build a ring to the tolerances that we can hold now and be able to deliver to you at a lower price. Imagine that in today's world of what, 30% inflation? I'm not buying the 6 or 8%. I'm just not buying it. But this is a dual disc grinding system, and this is literally just a couple of weeks old.
So, Lake, I got a question for you. Going back to that other machine, the question is does that machine monitor the sleeve OD and tell the operator when the sleeve is past tolerance spec?
I believe it does. It's looking at everything, it's feeling and sensing. It's like an automated hone, can sense and feel for the honing sleeve. It feels everything that's going on. If it doesn't like something, it says stop.
Okay, perfect.
This is lapping the OD or the thin flank, bringing it into spec. As you coil that wire, the ID is getting thicker and the OD is getting thinner, right?
You end up with a wedge. The ring becomes essentially what's known in the diesel world as a keystone ring. Because when you take a steel ring and you bend it, you're stretching the OD, compressing the ID. So you're actually building kind of a trapezoid, and you've got to bring that ring back into flat. And that's part of what this process is. And this is, so ultimately after it comes off here, we've already heat treated the part, we've gap sized it, we put the face profile on it, we've now set the thicknesses of the part. It's going to go to coating. Now, some of those coatings are done, can be PVD applied coatings, some parts are moly style coatings. We don't do that coating in-house, that's all done externally, but all the OD or the external profile coatings, with the exception of the oxide, is done in here. We also do on our diamond finish line an anti-friction coating on the top and the bottom flanks of the ring, known as WS2 or tungsten disulfide. That's actually done in a room back over here. That's real loud, kind of nasty, and a little bit on the messy side. But we also do that coating in-house. Now, it was asked earlier, somebody wanted to see the gas porting process, which now, don't take it wrong, folks, I could be wrong. I believe received its patent on April 26th. Yeah. So, but this is the gas porting area right here. So the rings are going to go in, multiple rings in the pallet, and we'll come around.
This is the magic truly happens. Gas ported rings are absolutely awesome. I've been involved in several tests now. I can even have in my own personal car. It's amazing what gas porting rings do. As you can see, the whole product. Both the of these machines do gas porting, right?
Yes. Right now, this one's set up making parts for our power ring filers that we build in house.
Yeah.
We're building pieces on that, but both of these machines will do that. And as you saw just a moment ago with Blake, we're constantly checking the tolerances on the parts as they're going through the shop. We're always looking at thicknesses. We're not going to wait till the end of a batch of parts to go, oh hey, those aren't any good. We're constantly checking parts as they go through the shop.
You got a gas ported ring that you can hold up to your focus.
You think, knowing for months ahead of time that we're doing this, that we might have some props and some things laid out ready to go. I don't know if we do or not.
Those are not gas.
Those are not gas ported yet, but it's coming. Up, here we go, right here.
Perfect. Oh yeah, good light too. So yeah, we can gas port steel rings, we can gas port iron rings.
Yeah, that
Change the size of the gas port.
absolutely different sizes of the gas port depending on the thickness of the ring. That ring I can tell you by looking at it, the hardened ductile iron, what's known as our TNT ring. In the sealed power world, known as the Hellfire ring. It's a martensitic hardened ductile. Very good ring for tough environments, nitrous engines. A lot of sprint car guys run this in the dirt world. It's a very, very tough piston ring, but that's a TNT ring that's now been gas ported on the top side. And for those of you that haven't or don't know it, having the advantage of the gas port in the ring, there's a few things. One, we're not putting the gas pressure loading point against the cylinder all the time. The gas port in the piston is stationary, so it's always concentrating that load. One of the things you'll see is specifically or particularly in like an injected alcohol engine, like a sprint car, if you look at the cylinder wear when it comes apart, you'll actually see higher wear lines that line up with all the gas ports in the piston. The beauty of this is the ring's always rotating. So we get a much more uniform pressure distribution around the cylinder wall. We don't get that accelerated wear. Other things that the gas ported ring helps to eliminate is reversion around the ring on the intake stroke. If you look at the gas ports on the piston and you see that black, gummy, nasty stuff coming back up out of the port, that's reversion. That's everything the ring on the intake stroke trying to pull the stuff that's below the rings back up, around, and through the ring and back into your nice, fresh, clean combustion chamber, in turn contaminating that clean intake chart, killing some power. The other wonderful thing is, because that ring's turning and rotating, the gas port is cleaning itself. It's not loading up and getting contaminated and sticking. I've seen quite a few rings come back that have got 15, 20, 30,000 street miles on them, and some LS twin turbo stuff. Absolutely beautiful. No contamination, no clogging, nothing at all. They're absolutely wonderful. So it helps to keep that gas port nice and clean.
I can say that to myself, right?
Yeah.
I've got a Forza Flat 6 that has gas ported top rings in it, and it's got 15, 20,000 miles on it, and we have, because it's a Forza, it's got an AOS, we can measure crankcase factor. So I can check it all the time, which I do, and it's losing nothing. So the gas port is staying clean, still affecting, doing their job.
Still doing their job. So what I'll do now is we're going to walk you down, kind of show you some of the inventory that we do. One of the things I like to say here is we make piston rings, not boxes of piston rings. Though we put our rings in a box, we're not limited to what comes in a box. If you look at some of the suppliers, you want, let's say you want a 1/16 top ring with a 5/64 second ring and a 3mm oil ring. We'll try to find a box that's got that in it. You got to buy 3 different boxes of stuff to get that. Well, that's not what we do here. Oh, and on the way, here's our Rottler 875A hone.
What's it doing? Honing lap and sleeve.
We run the nuggets off this thing. This machine will run between 10 and 14,000 strokes a day. If we're open, it's running. It's been an absolutely wonderful piece. As close to zero maintenance as you can imagine. We've had very, very little trouble with it. About the only thing I can remember, broke a belt once in the drive head, but they must have had about 1 million strokes on it at that point in time.
So, what's down here, Keith?
This is inventory. This is finished inventory in here. Last count, I believe Matt Hartford, our CEO and president, I believe he said we can do 31 million combinations of parts. As I said, we sell rings, not just boxes of rings. So if we get an order, we've got somebody with something exotic, and we get these every single day of the week. I had a gentleman the other day with a 1945 GMC inline 6, needed a 3/32, 3/32, 3/32, and a 3/16. Can't find them anywhere. Called everybody. I was like, man, let me get a look here. I don't know if we're going to have anything. I got into the system. We had 128 cylinders worth sitting on the shelf. Gosh knows how long they've been there, but we had them. This guy was elated. He was just so happy. He goes, you know how long I've been looking for these parts? So I'll throw kind of a catchphrase in there. Make me your first call, not your last. Don't wait 6 months and all the angst and anxiety trying to find those rings. Give us a call. If we don't have it, we'll make it for you. But this is all open stock inventory, from going from about 1.5 inches all the way up into the 13, 14-inch range. This is all finished parts. This used to be our airplane hangar back when the Moriarty family owned the company and Joe Sr. was still alive. Joe's had, I can't tell you how many airplanes have been through here, but now as we're growing and bringing in new equipment and new products into the place, we just simply needed the room. So unfortunately or sadly, no more airplanes.
Yeah, no airplanes had to be displaced for Piston.
Planes had to go. Yeah, so this is boxed inventory. This is the common popular stuff all ready to go out. You call up wanting a 16/16, 3/16 for a 4030 bore. Hey, it's on the shelf. It's ready to go. We just grab the box, put it in. Diamond finish rings are all down this same way. All the stuff that we built proprietary for specific customers. This is the packaging area. Orders get pulled downstairs, come up, we get packaged. Going to get put into the box again. We put it together your way. We're the Burger King of piston rings, and we're going to put it on the shipping belt, and we're going to send it down the line. So one of the other things, we'll kind of hit a little bit of inspection stuff here. Something that we do maybe a little different than everybody else. But this area right here is light tight inspection. One of the things that we're looking for is to make sure the ring is 100% light tight. So these are light tight gauges. These are known as mercury gauges. A lot of people make them. This particular one, I'm not exactly sure what size that one is.
4350.
That's the inside gauge, but 4567. But we're going to take that ring and we're going to put it in, and we're going to look for any kind of peripheral light. So if you want to come right over here and take a look. We're looking for any peripheral light that's around that ring to make sure that ring is 100% light tight.
Only lights at the gap.
Absolutely. Only lights at the gap, and that's where it's supposed to be. Some companies allow what they call 80% light tight, meaning 20% of the ring's not touching the wall. That's not how we do things around here. So unfortunately, again, because I wasn't ready, this is tangential load testing. When people ask us, how much, hey, 10-pound O-ring, 15-pound O-ring, 20-pound O-ring, what we're not doing is putting that ring into a cylinder and dragging it through with a fish scale. We're not doing that. That's a sliding friction test, which is actually a recognized SAE test. So we're measuring sliding friction. As a manufacturer, we don't have the luxury of having your cylinder in your block in our shop to tell us what that is.
Lube you're using as well.
And lube or no lube, a dry test or a wet test. So we have to actually be able to measure the force or the pound force that it takes to compress that ring down to a specific size. So we've got this machine. It's got a slip ring in it. Kind of looks like a transmission brake band. We're going to have a master. This one, I believe, looks like 4105. We're going to put that into the sleeve. I'm going to knock this loose. I'm going to set this for about 10 pounds of force. So I'm looking for it to be around 10, and it's pretty darn close. I'm going to take it, lock it so that the lead screw can't turn. Take the master out, and I really wish I had an oil ring here. But we're going to take that ring. It could be a compression ring, it could be an oil ring. I'm going to put that ring into this holder. We're going to set it into the master, into the slip ring. I'm going to put the vibrator on here, air operated. And what we're going to do is activate the machine, and it is going to shake and vibrate the holder that's holding the ring in question, whether it's oil ring or compression ring. Slip ring comes down to the bore size that we're looking for, and it's going to read to me in pound force what it took to compress that ring down to that particular size. Could be, 4-inch bore, 5-inch bore, who knows what it is. It's, whatever size it is. I don't even know what size this is. I'm looking for anything. That one might work. Let's just see if that'll go in there and do anything. It's going to bottom out in the holder. But just to give you an example of what it looks like. And here I am screwing the whole thing up. I'm just a train wreck.
Don't worry about it. Don't worry about
Yeah, it's only live. So this one's going to be all locked up. So, but just it's going to come down, squeeze down on the part. And this one, because it's all bound up, is over the range. This thing stops at 30 pounds. It's over limit. You're going to kill me. You're not doing it. You're killing me. So that's this particular machine. This machine goes from 0 to 30 pounds. This is a similar machine, but we use this particular one. This is set for 0 to 10. This is where all the thin, light tension stuff gets checked. This is where we check all the diamond finish rings, whether that be from the top end, NASCAR, Pro Stock, World Rally Car. They're all done on this machine. It's an electronic version of that machine, very similar. But we run the load cells 0 to 10 because the load cells are obviously, or maybe not obviously, they're the most sensitive in the middle of the range. This particular one, 0 to 30, it's most sensitive in the middle. This one's 0 to 10, most sensitive right in the middle. Most of the stuff that gets checked on here is going to be 5 or lower. Most of the stuff that gets checked on here is going to be 20 or lower. So we try to get the load cells right into the middle of their range.
By the way, having the oil ring tension is a big-time tuning tool, right? If it's heavy nitrous and you got a really great oil control, you need a really high oil ring tension, we can do that, dial it in, or maybe it's an NA deal where it needs to be super low, drag rate deal, you can get it down as low as you want it to go.
So these are all mercury gauges in here, different sizes. We have hundreds of these things, if not thousands of these in the shop, all different sizes. For light tight checking, ring inspection, gap setting. We can check your end gaps in here if a customer has a question on, oh, hey, my gap. These are accurate to the millionth. If this is 4125, for whatever size it is, it's dead on. So again, the math works. For every thou you change the bore, you change the ring, 0314 or pi. So if we've got something that's looking way off, we can always check it in one of the masters and know, oh, hey, brother, your bore size is actually 4 thou bigger than what you're thinking it is. These don't lie. They're very, very accurate. Yeah, we're going to show some tools. We built all our own tooling in-house, all our tools, I should say, in-house, from leak down testers, ring compressors, ring squaring tools. These are all sizes that are already produced and built on the shelf. Let's see here, ring square built in-house. Whoever's going to get this one's going to get ruined, and I'm already opening the box. All built here, laser marked in-house. And we do custom sizes. So if you ever need something that you don't see in the catalog or you don't see on the website, we can build it for you. It doesn't usually take but a few days. But in here is where we build the power ring filers. This is Brian Weaver, the world. Brian, looks like Brian's, what are you doing, Brian? Tabbing rails for Brian's. Actually putting
another interesting thing.
Another interesting thing.
Rails.
Ryan is actually putting a tab in the oil ring rail. So if you've got a flat engine like a Porsche or a Subaru, Volkswagen, you can actually put a locating notch into the oil ring groove to stop the oil ring rails from turning. You can tab them and position them so in like 3 o'clock, 9 o'clock, 10 o'clock, 2 o'clock, keeping the oil rails above the lower part of the cylinder, because once they get down low on a boxer style engine, fluid starts to pass through the rails and they're going to stay there. You've got a leak path that's going to just stay there. So tabbing the rails, we put an anti-rotation lock in them. And it's very simple, but it's very effective and it works extremely well. But this is ring filers. The other day I was in here, there was about 40 of these things going at once. But these are frames, mounts, motors. Let me see if I can find a finish one of these while Lake's panning on that.
Bearings, motors, plates. Ooh,
here's a candy apple red one for those who like a candy apple red one. But this is the finished product. We have to modify the motors, split the motors, fans to put drive ends on it. For whatever reason, we can't seem to get motors made the way we want them. So like all innovators, we do it ourselves, figure it out and do it. It's an extremely cost-effective machine. It's very, very fast. I'm no ring filing guru. The other weekend, a friend of mine's got a couple of 428 Fords. Fortunately, both the same bore size. I did 16 cylinders in 45 minutes. And like I said, I'm no Lightning McQueen here. So you imagine somebody can actually do it and do it fast.
These things are awesome. I love them. It makes ring grinding, filing so easy. It's like, yeah, gotta have it.
Yeah, absolutely, and all built right in-house. Yeah. So coming around this way, I can only show you a little bit of what's in this room. This is inspection. This is where all the, everything gets checked, all the real high-end stuff gets done. But we can show laser marking. We do all our own laser marking in-house, robotic arm, automatically loads and unloads, Nikon video microscope. This will see light that the human eye cannot. So we do light tight inspection, as you saw out there earlier in ambient light. We also have 2 dark rooms, so no light whatsoever doing light tight inspection. But we also use the VMR. This can see, as I just said, this can see things that the human eye cannot see. So we can look at light tight to a level that, again, the human eye cannot detect. These are Taylor-Hobson profilometers, so we can, we talk about using profilometers all the time, but we're always talking about cylinder surfaces, cylinder finishes. These are actually used to measure the profiles on the rings. We can look at the face profile, flatness, parallelism. We can look at, rings that we do with multiple profiles on it. It may be a combination or an offset barrel. It may have a leading scraping edge on it. This is so we measure these in the Taylor-Hobsons. We've used optical, microscopes. We've used, USB style microscopes, but these go to a level of detail that we've yet to be able to accomplish using that type of technology, though I'm sure it's out there. We just haven't found it yet. So over here, we've also got the ability to measure helix or twist that's in the ring. We can actually put a ring in and actually put dial indicators on it. Some people, when you talk about minutes of twist, how much axial rotation, when you look at the bevels that are in a ring, whether the bevel's on the top of the top ring or the bottom of the second ring, it's there to induce twist. It's there to make the ring rotate. I'm going to use this ring, which I probably ought to not, but when you take a ring and close it down and you've got that bevel, you're going to notice the ring rotates or it twists like a Belleville washer. And we can actually control that amount of twist by how the ring's coiled in its, in itself from a material point of view. But at putting the bevels in, putting that chamfer in, we can induce more twist, less twist, twisting up, twisting down.
This little device here, this little holder lets you actually measure.
We can actually come in and measure all that in this. With the ring in there, we can actually measure how many minutes of twist it has. Microscope, more tangential load testing in here. This one goes even to a level of detail that the ones outside is beyond. These are the things that I can show you in here. There's other things in here that I can't talk about.
Right, that's why the camera is like moving around very weirdly. Yeah. It's not that I am a bad camera person. Yeah, I am, but I also know there's things I can't show you in here, so I'm making sure you don't see things you can't see.
Yeah.
Or shouldn't see.
Or you shouldn't see, because both of us being on the carpet shortly.
Right, yeah.
Hey, Lake, got a question for you while you're in that room there. Yeah, will that profilometer measure waviness?
The waviness?
Oh, yes.
Yes, 100% it can measure waviness, no doubt.
Okay, and the next question was, is the twist only on steel rings, or is it on all rings?
Well, any ring with the bevel will have twist.
Yes.
Well, and a Napier, right? Anything you cut a Napier in it that undercut.
Well, let's
twist, right?
let's walk this way real quick, since we're on that subject.
Okay.
And hopefully the production meeting's done. We're coming into the office section. This is our CEO and president, Matt Hartford, walking down the hall. NHRA, multiple NHRA race event winner, pro stock winner. This is our conference room. Communication, training, resources, and support. But when we talk about the twist, if you think about a piston ring, we'll put it into some quadrants. This is the face, that's a barrel face ring. That's the cylinder wall. So I'm going to slice it into what I'll call 4 quadrants. This would be the inside edge of your groove. This would be the face of the cylinder wall. So if I come in and put a bevel on this edge, which contrary to what a lot of people think that's there to help get gas pressure in, though it does allow it, its real function is to induce twist. So removing material out of what I'll call quadrant 1 is going to want to make the ring twist upwards, or positive twist. So with the same said, if I come into quadrant 2, this outer edge, and if I were to cut away material in here, it's going to want to make the ring twist down or have a negative twist. We rarely ever do any kind of modifications out here. Sometimes we'll do what's referred to as a Dykes ring, a stepped ring, like you would have in a blown alcohol engine. That will affect twist. But primarily, twist is induced in quadrants 1 or quadrants 3. So if I was doing a second ring, a tapered face second ring, excuse my rude, crude drawings here, and I come in here and I put that bevel here, I'm going to induce reverse, or what's referred to as reverse torsional twist. I am going to make that ring want to twist downwards, so that on the upstroke, the ring is paralleling the bore, and on the downstroke, it's acting as a scraping effect. So the ring's rotating in the ringland. But the same thing happens out at the face of the ring. If I cut a Napier in it, if I come in here and I remove material from here, this acts the same as removing material from number one. I actually start to induce positive twist. The other one that we do is when we make a gapless ring. We're going to come in and we're going to cut a step into the ring to produce our gapless. This will also induce some positive twists. So sometimes when you see a gapless top ring, you'll actually see the bevel on the bottom. And what we're doing here, just like we talked about in the inspection room, is we're trying to control the amount of twist. When we came in here and cut it gapless, we induced positive twist. But we may have induced a little too much. So we'll come in, put a little chamfer on that inner lower to help to offset some of that twist. We're still inducing positive twist. We just want to take a little bit of it out. What can happen if it's got too much twist either direction? Especially if you've got very tight ring to ring groove clearances, you can get a ring that's very sticky or tight in the ringland. The ring should always turn freely in the groove. A quick test for that is take a ring, whatever ring that is, ours or someone else's, compress it down like it would be in the cylinder, rotate it on the piston in the land, make sure the ring turns nice and smoothly. If you feel a ring that's very tight, very sticky, you more than likely have a ring that's got too much twist for the amount of ring to ring groove clearance you have. The tighter that clearance is, the less twist you'll run in the ring. Typically, once we start getting into what I'll call the high-end tolerances, 6/10 clearance, 8/10 clearance, 4/10, very tight clearances, we don't induce any twist into the ring at that. There, it's a neutral ring because any twist is going to make the ring too tight in the land when it's in a compressed position. So that's a quick explanation about what that bevel does, inducing twist, positive or reverse, into the ring. Just happened to be good timing because we were right here by the conference room.
All right, so Rob, we got any other questions left? Because now we're about an hour and 15 minutes into this, and we're here with Keith and a whiteboard. So if there's a time for a question, probably is now.
Okay, so there is a couple questions. The one is, are there different surface finishes on the sleeves depending on what ring material or style will be broke in with? I think they're referring to the lapping sleeves.
Yes, there is. Depending on what the material is, if it's a tool steel ring, it'll have a more aggressive finish on it to accelerate the process. So yes, depending on what we're doing, we can and sometimes vary it. Now, generally speaking, no, they're all basically done the same. But if we know we're doing a run of a specific part, then yes, we may change that finish that's on that, just like you would on your engine. If you're building an engine, you're going to run tool steel rings, you're not going to hone it the same as you are with a 0.8 millimeter diamond finish ring. It's two different types of materials, two different coatings. So we do address that here at the same time.
Okay, all right. Here's a gapless question for you. They mentioned they ran, in the early 70s, they ran the gapless rings in a drag race engine and it worked fine. Today, with all the testing being done, some people removed them from the second groove and found more power on the dyno and racetrack. Something to do with keeping the top ring sealed. I was wondering what you guys know about this subject.
I don't know if you were. I don't know if you were chiming in or no.
Oh, okay.
What you've got here, folks, is Total Seal started off with a ring in the top groove. The gapless ring was in the top groove when we started. As time progressed on into the 70s, kind of early 80s, we were having problems with the top rings failing. So they moved to the second ring groove is what, the evolution of the company. Late 1990s, I came onto the company. Matt Hartford came in a little bit after me, about a year after myself, and we started playing with the gapless top ring again. What we found, and this, the research and development, the R&D that, should have been done or could have been done, it just wasn't figured out in the early days. And what we found is the gapless top ring, stopping all the heat in the crown of the piston, needed more room to grow. We couldn't gap the ring with traditional gapping specs. Matt and myself, a gentleman by the name of Mylan Kiesler in Maryville, Tennessee, kept working with these rings on the dyno. We get on there, get enough heat in the engine, all of a sudden she'd start to go to pressure. It's like, hey, what's going on? Get it apart. Wow, it butted the rings. Open the gap up some more. Run it. We went further. We'd go more pulls, and then it would do the same thing. And ultimately, the light bulb went off. Says, you know what? This thing's stopping all the heat right in the crown of the piston. It needs a lot more room to grow. So we really opened up that end gap, and voila, it stopped. No more problems with butting the top ring. The other things that it does very well on the top is it draws harder on the intake stroke. It fills the cylinder better. If you've got a carburetor, it hits the carburetor much, much harder. I had a gentleman yesterday that I was talking to. He has a big inch Pontiac engine. He had the Gapless top rings in it. He put a conventional set of rings in it, called me up. It's a dry sump engine making vacuum. It doesn't make anywhere the amount of vacuum that it made before, and it's down about 30 horsepower. And he's looking at brake specifics, how it's pulling air, how it's pulling fuel. We talked about, I said, all your power is just sitting right there, how it affected the intake stroke on that engine. So that's where the Gapless top really shines, is in an NA motor and how it affects the intake stroke. A lot of people like to talk about blow-by and leakage, which is very, very effective in eliminating those and reducing those, but it really signals much harder on the intake stroke. Now, as far as the conversation about Gapless top ring versus Gapless second ring, that's up to the end user. That's a personal preference kind of thing. Lake standing behind the camera right now is a very, very good friend of Ron Shaver's, Shaver Specialties. I remember when we came out with the Gapless top ring, sent some to Ron. Ron ran them, said, hey, they work just fine. I'll have Gapless second rings. I've been using them for decades. They work fantastic. I have no issues with them. 9,000 RPM, 15 to 1 compression, sprint car engines, no issues. I'm staying with Gapless second ring. So it's kind of a personal preference thing. We can sit and talk about and discuss, ring flutter and things like that. It's a very misdiagnosed phenomenon. Most people that like to say they have a ring flutter problem really just have a blow-by problem or a leakage problem. You really have to look at, pan pressures, what's happening near peak torque. There's a lot of things. Ring flutters, cylinder finishes, Lake just said, piston rock. It's one of the most self-misdiagnosed things out there. It's like going on WebMD and I got the sniffles. Well, of course, you're going to die from it because that's one of the side effects of the sniffles. Just go check it. Same thing with ring flutter.
Okay, super, guys. Okay, I'm going to try and ask. A couple of these questions are pretty technical, and if I don't get it right or I don't read it right, I can always forward them along, but I'll give it a go here. So they're asking, what's the difference between radial and tangential load, and how is radial load measured?
Well, I think it's the same thing. Yeah. They're really looking at the radial load is the same thing as tangential load because it's the force the ring is producing in the lateral direction. When Keith was mentioning about the fish scale, when you're doing the fish scale, you're literally pulling. I think I'm gonna turn myself around so you can see me. Hang on a second here. Right. Come on. There we go. All right. So when you're doing the fish scale, you're pulling it up. It's sliding friction. You're not. Of course, the radial tension is part of that, but the surface finish, the lube you're using, the amount of lube you're using, the coating on the face of the ring, all of that is factoring into what that friction test is. And so that friction test isn't the same as a tangential load. The tangential load meter, radial, tangential, so all lateral direction, it's just basically measuring the spring force, if you will, of the assembly. That's different than the sliding friction of the assembly. So hopefully that answers their question in a way that they appreciate.
Perfect. Okay. Next question.
I'll just say, he is Lake Speed.
Do you know what the proper ratio of end gap is of the top ring to second ring in, let's say, NHRA stock application?
Hold on a second, Rob. Someone's trying to call my phone. Of course, I'm using my phone to listen to your questions. So hang on 1 second.
Okay. Yep.
I'm going to put this down just 1 second. Make them go away. Okay. Sorry. All right. Now,
all right.
You can ask a question again.
Hit us with that again.
Okay. All right. So they're asking, what is the proper ratio of end gap of top ring to second ring in like NHRA stock?
That really depends, again, on temperature of how the engines run. End gaps really come down to how hot you're getting the part. You know, where I gap them as far as the actual size goes really depends on the temperature of the engine. But in an NHRA stocker, I will typically run the top ring at about a bore size of bore times about 4 to 4.5 thousandths per inch of bore. This is assuming it's not a chilled engine. It's, you know, it's a not, you know, they're not freezing.
Driving it up to the stage.
Yeah, you're driving up the stage lanes, doing your thing. You might see 180 degree of water temperature. Yeah. Hey, hang on just one second.
You guys all done out there?
Yes, we're done out there. Thank you.
Cool.
But sorry, quick question there. But typically you're going to be about 4 to 4.5 thousandths per inch of bore in that normal temperature range. Now, as far as the second rings go, the big second ring end gap thing, I'm not opposed to that. But I'm also not an advocate of that. I'm not one of these people that say, oh, you've got to have 20% bigger end gap on the second ring, 30% bigger on the second ring. It really comes down to, you know, how much pressure is getting by the top ring. One of the, you know, and I stand in this camp, you know, if I have to open the second ring up egregiously to settle the top ring down because I've got a blow-by problem, I'm looking at the wrong end of the horse. I need to figure out why that much pressure is getting by the top ring. I could show you data after data after data showing engines gapped at 4 thou per inch on the top ring groove, 3 thou per inch on the second ring groove that have absolutely zero ring flutter issue, incredible ring seal, and vice versa. I've seen engines that required a larger second ring gap because the top ring's not doing the job that it should be doing. If you remember back traditionally, for 100 plus years, we've gapped the second rings tighter than the top ring. And guess what? They work just fine. My dad's Vega in 1976 did not have a ring flutter problem because the second rings were tighter than the top. Now, granted, it probably wore that Alucil bore out because GM didn't use chromed rings as they require, but that's a whole different thing. So it really comes down to the specific application and how much gas pressure is getting by the top ring. Gapping the second ring the same as the top or a little bit bigger than the top, I have no problem with that. But if you have an engine that needs a really big second ring gap, 40, 50, 60 thousandths, to get it to settle down, again, we need to be looking at the top ring because there's, you know, we're looking at the wrong end of the horse. There shouldn't be that much pressure getting by the top ring in the first place.
I'm going to throw you one more variable in there too. Oil ring tension.
Oil ring tension, yeah.
So I have seen in my limited experience here, having a slightly more, not tons more second ring gap, but a little more ring gap on the second with a low tension oil ring seems to actually improve blow by, which seems completely counterintuitive until you think about the fact that maybe that extra little bit of blow by you're getting there is actually with a very small, thin, light oil tension oil ring is actually using the gas pressure to push the oil back through the oil return grooves in the oil ring so that you're getting better scraping because you're basically using that little bit of leak to assist the oil ring.
Lake's 100% correct on this. There are later model engines. Now, yeah, we'll go back to tensions. I mean, you look back at a 350 built in 1970, you know, it had a 560 force, 316. So you're talking compression rings that were 6-7 pounds of force each and an oil ring that was 20 to 25 pounds of force. It did what it needed to do pretty much from a mechanical point of view. But in the modern engines, again, trying to get those tailpipe emissions down, trying to get that fuel economy up, you know, we got to get it there, keep those electric cars from taking over.
The oil ring tensions have gone down.
The oil ring tensions, as Lake just said, have gone down. We've got to get that friction out of there to get the mileage up, get the tailpipe emissions down. And one of the ways you can do this, think about it like a dry sump engine, but backwards. You know, so if you've got a dry sump engine and we're running a very, very light oil ring, one that won't necessarily keep it dry without that vacuum, we're using that dry sump to help evacuate oil down that cylinder, pull oil down out of that oil ring. If we kind of go the other direction in a wet sump engine and I open that second ring gap up and induce, we'll say, higher than normal pressures across that oil ring, we're actually pushing the oil down the cylinder, kind of like, I'll say like a dry sump backwards. In reverse.
I think that's a great analogy to think about that as a dry sump. Say with a dry sump, you don't need to do that because it's pulling down. With a wet sump, you can kind of simulate that with a low tension ring by flipping it over and using a little bit of blow by to basically do the same thing. So pushing versus pulling.
So that's a way of, we'll say, in the modern engines, you can see some pretty incredibly light oil ring tensions, these things from the factory, but they're running a really large second ring gap to try to get that a little bit of that extra pressure across the oil ring to make that 7. Think about it, folks. I mean, there's OE applications out there with 7-pound oil rings in there today. I mean, 10 years ago, that's what you ran with a 5-stage dry sump. Today, they're in, NA motors, wet sump.
Right. And I think this is a great point that it ends up being a really great question, is that if you understand the system, that all three rings are working as a tandem, and that these are the different levers you can pull, there's not a one right answer. It's understanding the complete system, understanding that application. So then as the engine builder, you know what levers to pull to get the results you want for your application.
Yeah, no one size fits all.
No, that's the key thing, What else you got, Rob?
All right. Sure. Next question is, they're asking if the nitrous ring can be used for a street engine for better sealing, even if they're not running nitrous.
Oh, you certainly can. The things to consider that a dedicated nitrous ring generally doesn't have anti-friction coatings on it, like our tool steel rings generally don't have any kind of anti-friction or anti-wear coatings, though they can. The biggest thing there is, could you put that part in there? Yeah, but if it's going to go in and stay in there for a long time, you want to make sure it's got a good anti-friction coating on it, because that's going to reduce wear in the cylinder, increase the longevity. It's that's kind of an important thing if it's going to go in there. So yeah, having that base material be overkill, I guess it's like putting a Bryant crank in your Pinto. It's okay, it doesn't hurt anything. It's just overkill.
I'll say one thing to be careful of is back to oil ring tension.
Yeah.
Typically with nitrous stuff, because oil has a lower octane value than fuel more times than not. There are a few rare exceptions that don't apply to most people, right? The oil in the combustion chamber is generally a bad idea. So with nitrous engines, because they typically run a very heavy viscosity oil, we run really high oil ring tensions. High oil ring tension is going to generate a lot of heat, a lot of friction, a lot of wear in your cylinder. Not the best option for a street motor.
Yeah.
Material, great choice.
Right.
Could be overkill.
Yep.
Probably is overkill. Oil ring tension is probably a big no-no.
Yeah, more than likely.
Not going to be happy with that.
All right, super. What I'm going to do, guys, I got one more question for you, and then I'll end up sending you the rest of the questions just so we can respect everybody's time.
Sure.
So this one here is reusing used piston rings. Why not?
Why and why not on reused piston rings?
Well, that one really comes down to how much use they've had and how worn they are. The things that you want, and I'll wrap this around, is the same thing as having a used piston. The thing is, if the ring is lightly worn, the faces, you haven't worn the profile off the face, you haven't worn the second ring flat, you haven't worn the barrel off the top ring, they are certainly reusable. If they're holding their tension well, they haven't collapsed or creeped, annealed, you can certainly reuse them, but you need to take some measurements. Don't just arbitrarily grab them and throw them back in. You want to take a little time and look at the parts and make sure the part is a reusable part. Same thing goes with pistons. You need to be looking, not just, have guys take a used piston and they'll throw a caliper across the skirt and go, oh yeah, she's good. Well, you really need to be looking at the ring grooves themselves. You need to take some gauge pins, and I prefer the gauge pin because it's a very accurate tool, and check your ring grooves. Ring grooves will get a lot of wear in them that you can't see with your eye. We'll go to the whiteboard real quick. These surfaces should be parallel. But you would be amazed at how many times I see a ring groove that comes out that looks like this. Now, this is exaggerated for the whiteboard, but you'll take a gauge pin and put it in this one. Let's say you've got an 043 groove. Look at the job card on the piston. It says the groove's cut 044. Well, you stick an 044 gauge pin in there, and it's nice and snug. It doesn't wiggle up and down. It goes in. It's nice and smooth and uniform all the way around the piston. You've got a pretty good ring groove. But if you take that 044 gauge pin, stick it in there, and I can wiggle this thing up and down like a teeter-totter, you've got a wear pattern to the bottom of the ring. You've got a taper worn in the bottom of the ring, land in the piston, and the ring, you could even re-ring it, use your old ring. It's more than likely not going to come back into that. It's not going to reseat to that. So it's really about measuring the parts when they come apart. If the parts measure good, they check good, profiles look good, you're perfectly able to reuse them again. So hopefully that answers the question.
All right, guys. Well, that was just incredible. Great job. Always, especially that some of that new equipment that you've got. Where we saw a bit of a tease of that last year when we were there for the tour. Now you got the whole production run going there. So, like I say, like I'll pass along any of the questions that we didn't get a chance to answer. For those folks that are listening, we are going to have a recording of this on our YouTube channel coming up, and Amanda will show you how to do that. So. Again, really appreciate your guys' time. We know you're busy. If I was down there, it'd just about be lunchtime for you, so we'd go for lunch. But that's just the way virtual is. So, Lake, and I guess we'll see you.
Right? No one had to come to Leo see this. That's what's great. You can be watching from anywhere in the world right now.
Yeah.
Or watch the recording at some time and see. This is how you make piston rings.
Exactly. Yeah, no, thanks again, and I guess Lake, we're going to see you in about a week and a bit out at SCAT. So
less than 2 weeks, we'll be at SCAT, and we're going to have some great things to talk about.
Exactly. So, guys, I'll let you get on with your day. Thanks again, Keith. I know you're busy. I really appreciate the tour, and this was first class. Thank you very much.
Thanks, guys.
Thanks for having us. It was a blast.